Welcome to the Explainer. You ever wonder why a spoon can show you two completely different reflections? Or why a straw in a glass of water looks like it's broken? Well, today we're diving into the fascinating physics of light to figure out the secrets behind how it bounces, how it bends, and ultimately how we see the world. So we'll kick things off with a straight line path of light that makes sight even possible. Then we'll explore the kind of funhouse world of curved mirrors. After that, we'll check out what happens when light actually bends through different materials. And finally, we'll see how we can harness that power to understand how lenses work. So let's get into it. All right, let's start with a question that seems really simple on the surface, but it's actually the key to everything else we're going to talk about. What is it that actually makes things visible? I mean, think about it. In a pitch black room, you see absolutely nothing. You flip a switch, and suddenly the whole world appears. Why? Well, the answer is surprisingly simple, and it all boils down to reflection.
Here's the really crucial part. We don't actually see objects. What we're seeing is the light that bounces or, reflects off of them and then travels into our eyes. And pretty much all the time, that light travels in a perfectly straight line.
Okay, but this is where things get really interesting. What happens when we start to bend the rules, or in this case, the surfaces that light reflects from? This is where light starts to play some cool tricks on us and where we really learn how to control it. You know, you've already done this experiment, probably in your own kitchen. You look into the front of a spoon and your reflection looks one way, you flip it over and it's completely different. That's because a spoon is a perfect everyday example of two types of curved mirrors. So let's give these surfaces their proper names. A concave mirror curves inward. An easy way to remember this is it's shaped like a cave. A convex mirror, on the other hand, bulges outward. Simple enough, right? But to really unlock how they create such different images, we need to map out a few of their key features. First up, let's find our starting point. The exact geometric center of the mirror's surface is called the pole, and we label it with a P. Just think of it as the anchor for all our measurements. Now, I want you to imagine that our curved mirror is just one little slice of a giant, complete sphere. The center of that imaginary sphere, that's what we call the center of curvature, or C. It's a super important point that's actually outside the mirror itself. And if we just draw a straight line that connects our first 2 points, the pole and the center of curvature, we get what's called the principal axis. This imaginary line is basically the backbone for figuring out everything that mirror is going to do. And right here, this is where the magic happens. Just look at how these two different mirrors treat parallel rays of light. The concave mirror on the left, it acts like a collector, gathering up all the rays and focusing them down to a single point. This is the whole idea behind satellite dishes. Then the convex mirror on the right does the complete opposite. It scatters the light, making it look like it's spreading out from a point behind the mirror. That special point where the rays all meet, or at least appear to meet, has a name. It's the principal focus, and we label it F. Seriously, understanding where this point is located is the secret to predicting exactly what kind of image a mirror will create. Okay, so now that we have those terms down, let's see how they all come together to create the images we actually see. Because, depending on the type of mirror and where you place an object, the results can be completely different. Now, don't worry about memorizing this whole chart. The key thing to see here is just how versatile a concave mirror really is. Depending on where you place an object, the image it makes can be tiny, it can be the same size, or it can be huge. It can be upside down and real, which just means the image could actually be projected onto a screen, or it can be upright and virtual, meaning it only appears to be inside the mirror. So far, we've only talked about light bouncing off of surfaces. But what happens when it passes from one medium into another? Like from the air all around us into a block of glass. Look really closely at the path this light ray takes. It's fascinating. As soon as it enters the glass from the air, its path bends. Then, when it leaves the glass and goes back into the air, it bends again. So this journey is definitely not a straight line. This bending of light is called refraction. And it's responsible for so many things we see every single day, from the way your glasses correct your vision to, why that straw in a glass of water looks like it's broken right at the surface. And, this bending isn't random at all. It's incredibly predictable. It follows these very precise physical laws. In fact, there's a formula that lets physicists calculate exactly how much the light will bend when it moves between any two materials, say from air to water or water to glass. So if we can predict how light bends,
Can we control it? Oh, absolutely. And we do it by precisely shaping transparent materials like glass. This is exactly how we harness the power of refraction to create lenses.
We actually measure a lens's ability to bend light by what we call its power. A lens with high power bends light very sharply, which brings it to a focus over a really short distance. A low-power lens bends it more gently. And mathematically, it's just the reciprocal of its focal length.
The unit for this power is the diopter. And if you've ever had an eye exam and the doctor told you your prescription is, say, +2 or -3, they were talking about diopters. They were measuring the exact power of the lens you need to perfectly focus light on your retina. But for all of these predictable rules we've just talked about, the fundamental nature of light itself, well, that was a huge mystery for centuries. Is it a wave, like sound, or is it a stream of tiny little particles? The totally mind-bending answer from modern physics is that it's somehow, mysteriously, both at the same time.
It just goes to show you that even the most basic things we experience, like simply seeing the world, are built on these layers of incredible physical complexity. It really makes you wonder what other common things that we see every day are way more complex than they seem. Thanks for tuning in.